Lorenzo can start.
Okay, so can you hear me?
Yes.
Excellent. So give me a second and I'll try to share the screen. First I have to open. I'm sure I'll make it. Okay. So
can you make it full screen?
I should be able to make it full screen, but I'm having just a small problem because it's covered by
You can maybe unshare, then go full screen and then share.
Yeah, I'll try that. No, that actually, sorry, but it doesn't work because then I don't see the Zoom anymore. So let me try again. So let me see. No, that didn't work.
Maybe play.
Yeah, that's you know, I know, but I cannot click on play because the Zoom bar is too big and I don't know how to move it.
I see.
So, yeah.
Do you guys know how to do that?
Right.
Okay, no, wait. I made it.
Okay.
I didn't know that the Zoom bar was actually movable. So.
Okay, fantastic. So now we can start a panel discussion, the last one of this workshop. And we're very happy to have Lorenzo Magnea from the University of Torino, who will tell us about non-abelian infrared divergences on the oscillation sphere. Take it away.
Yeah. Let me also start the video so that hopefully you can see me. As well as hear me. Yeah. Can you also see me?
Yeah.
Can you see the mouse?
Yeah.
Hey, fantastic! Everything's working. Yeah. So thanks for the invitation. It is a pleasure to be here, and I have to say, even though I couldn't really follow for the whole week, I learned a lot from this workshop. So I want to be brief. I don't want to steal time from the discussion. So let me just emphasize a few things. First, what I'm going to say, which is going to be very brief, comes from a somewhat different perspective. I mean, what I do for a living is really studying infrared divergences, having in mind collider application, and in that community, the potential interest is really always whether some new techniques can be, developed to enable, high order calculations, which are what is needed there. And so, that's my background, which also means that there is a lot of stuff that you guys know very well, and I really don't. So what I will say, a second caveat, is just perturbative. However, in the non-abelian context, we have all order results, and so actually the results most of the results that I will show are two all orders in perturbation theory. And third, I'm working strictly at leading power, so I'm going to be talking about soft theorems and collinear as well, but not next to soft or next to soft. And finally, I'm not taking a Mellin transform, but I think most of what I will say translates rather smoothly. And here I'm referring to what Hernan discussed the other day, but I think also Monica showed that the Mellinization of the factorization theorem works rather well. Okay, so I'm just going to give you a 2-minute blitz of what we know about the infrared factorization scattering amplitudes, non-abelian case to all orders. And then I will, take a look at what that actually looks like on the celestial sphere. And then I will take a stab at identifying the actual conformal field theory, which generates these results. So, okay, there are quite a few formulas on the slides, but I'll try to sort of, don't be bothered. I'll try to guide you to the essential features. So the first formula here was shown already by Hernan, and of course it's valid in QAD as well, but this is the non-abelian case. So this is an endpoint scattering amplitude, and all the infrared divergences are in this Z factor here, and then the rest is fine. Now in a generic massless non-abelian gauge theory, we actually know a lot about this Z factor. For example, we know that we can just write it as the exponential of a soft anomalous dimension, which is a color operator in the non-abelian case. And this particular way to write it is very practical and in my view also quite elegant. So I am implicitly using, rather explicitly using dimensional regularization. And the gamma n is a finite color operator. And every single infrared divergence arises from the scale integration down to 0. So I'm integrating to 0 scale, and the reason I can do that is because I'm using dimensional regularization and the d-dimensional beta function with d equals 4 minus 2 epsilon and negative epsilon. So as I said, we know quite a lot about this object. We really have all order information. And the information that we have is quite interesting in this context. So first there is a dipole term, which has contributions to all orders, and there's only color correlations between pairs of particles. And then the main correction is actually quite a high order correction. It only starts with 3 loops and only with 4 particles. And it is interesting because it is conformal. So it is a function of conformal cross ratio. I emphasize this is only true for massless gauge theories. And then there is a second set of corrections to this formula that I'm not going to discuss at all. It has to do with the fact that there are terms that are proportional to higher order Casimir eigenvalues of the gauge algebra, and that's a different story. It starts at 4 loops. So, okay, I need to say a few words about notation, because I said that this Zn here is a color operator. And the way we treat color operators is by introducing these capital T's here. And the capital T's are really just matrices in suitable gauge group representation. And they arise just from the 3-level factorization in a sense, right? So a soft photon or a soft gluon can only be emitted from the external legs. So it is just really a factor out here. And then to leading power, as I said, what factorizes is actually the amplitude without radiation. And this is just a color operator acting on this object. And these color operators are really nice because they, of course, they satisfy the gauge algebra. And they have a natural product. They square to the quadratic Casimir. And most interestingly, when considered as operators acting on the amplitude, like here, they are like momentum. So as operators, they sum to 0, or if you prefer, the amplitude has a support on the color conserving configuration. So this is really gauging. Now, in that language, this dipole thing that I wrote, one can write it in this way, and you see it's really a very, very simple object. And briefly, people hoped that this was actually the answer to all order perturbation theory. Then we learned about corrections. So you see, this color structure here, Ti.Tj, is really just one gluon attaching between 2 legs, and this is what you get at 1 loop. The surprise is that it actually generalizes, and in a massless theory at 2 loops, this has no corrections. And you see that all orders are here because this gamma k in front is the cusp anomalous dimension with the Casimir factored out. And these are just field anomalous dimensions that are responsible for collinear divergences. And as I said, this is everything. But at 3 loops, there are corrections that have a conformality property, and they start off with quadrupoles, and this precise expression, which is a beautiful expression, has been computed 5 or 6 years ago by these people. The Coulomb phase was mentioned a moment ago. So the phases here arise from this thing here. These lambda ij's are either 0 or 1. And for example, if all the particles are outgoing, they are 1. And so you get the log of minus Sij, and that's where the phases come from. So what happens to this when we go celestial? So this is a picture of Dante and Virgil in a classic illustration of the Divina Commedia, when they are actually looking at the celestial sphere, so you can see what it looks like. So let me first do a completely trivial manipulation. So I have this dipole expression, and I'm going to have to integrate over the scale. So that's why I call it lambda here, because it's the integration value. Now things simplify if I introduce a fixed scale mu, which is some fixed large renormalization scale mu, and then I write log lambda as log mu plus log lambda over mu. And then if you do that, then you see the first nice application of color conservation, because you can actually do the sum. At some point, you get this log, and you can do the sum over j, which gives you minus ti, so you get a number. And so you see that the color correlations are actually simpler. And so I have a correlated matrix here. And the rest, so the second line is color sync, okay? And in the language that we normally use, we would say that the first line gives a single, purely soft poles, whereas the second line gives collinear poles, and the last term is responsible for soft collinear double poles. And below you see how the poles are generated. The d-dimensional random coupling has a scale factor. When you integrate that, it gives you a pole, but let me not waste time on that. Now I do what your community has taught us to do, especially. Yeah, here we go. So this coordinate transformation, this choice of coordinate is just bringing us to the celestial sphere. And of course, you all know much more than I do about this. However, as Monica just showed, this gives a simple expression for the Mandelstam invariance. So the log just falls into pieces. And then what is interesting in the non-abelian case is that all these pieces that depend either only on I or only on J or just numbers, for all those pieces, you can do the color sum, and they drop out of color correlations, and you are left only with this term. So there is a slightly more complicated color singlet part here. And the real nice result is that the color correlated part becomes beautifully simple, and it is a natural generalization of what Monica just showed in QED. But let me emphasize again, this formula here is an all-order formula, and it's not, in QED in some sense, the all-order result is one loop exact, so it's the exponentiation of one loop. In QCD, this is certainly not the case, but we see here that something beautiful is happening. So the loop corrections somehow have factorized from the kinematic and the color dependence. And because the scale dependence is only here, then I can actually, at least formally, do the integral, right? So I can literally compute in the non-abelian theory, at least the dipole part of the infrared factor, and I just get an exponential that has the same structure that we could have in QED, but here in front, there is this function k, which is this integral here. And the people who work in perturbative QCD, they know about k since a long time. So k, for example, is the Regge trajectory in the high energy limit up to some matters of definition. K appears in the Sudakov form factor for quarks and gluons. K is responsible for Coulomb phases. K is really an old friend, which we can write as here in the left, and in n equals 4 super young mills, it actually has a very simple expression with only single poles. So let me emphasize this. This thing here, this formula, even if I didn't go on to do anything conformal, for the community from which I come, this is already very interesting, because this kind of complete factorization people hadn't realized. And this is just a consequence of having used the celestial coordinates. This kind of factorization had been seen in the high energy limit, where k is the Regge trajectory. But this is much more general. The energy dependence has gone into the collinearly into the color uncorrelated part. And so this is actually a nice result just in QCD. And then we can see what happens if we try to interpret this in the light of celestial logic, that there should be a conformal theory. And here, when I approached this, I approached it like a person who didn't know much about conformality theory, although I did double in string theory some years ago. And personally, I got a suggestion from this paper, but then later I realized that essentially the same result had been around for a while. And this is what Monica showed, right? That in QED, the logarithm of the soft factor is just the exponential of the log of the distances. And you can get this as a correlator of conformal fields. And indeed, you know exactly which conformal fields. And here there is no question of which is the conformal field. It's a free boson, right? The only strange thing is that the coefficient, instead of being a momentum, is a charge. That being said, it would appear at first sight that you are never going to be able to make this non-abelian because of all the intricacy of the correlation between color and kinematics. But what we saw before suggests that indeed it may be possible. And so you take a stab, and again, everything on this slide is fairly trivial to most of you. You just take a set of free bosons in the Lie algebra. So A is a Lie algebra index for SUN. So there are n squared minus one of those in SUN. Let me just emphasize two things. So one is that it really feels natural to organize these three bosons into a matrix using the generators of the gauge group in some representation. However, for the purposes of what we are going to do, this requires some care because these matrices are really supposed to be sitting at the end of some Wilson lines. And so they depend on Z. And when they are at different points, they must commute, but they don't commute anymore when they are sitting on the same point. So this is, fortunately, to get to the results that I'm going to show in a second, one really doesn't need to worry about this, but it should be kept in mind for future developments. And last thing I'm going to say on this slide is to note that there is, of course, a multiplet of currents, which are just Goldstone currents due to the fact that this action has only derivatives. And they are conserved currents, and they will, of course, also in the non-abelian case, give us a soft field. And then comes, if you want, the only strange thing about all this, that one is strongly tempted, let us say, to define a vertex operator, which instead of momentum has a charge, and instead of an abelian charge has a non-abelian charge. So that's this T operator, which I remind you depends on the point. And of course, one thinks, okay, so this is a matrix, right? This is, of course, an operator in the conformal Hilbert space, but this is also just a matrix and some representation of the gauge group. So does this make sense? I mean, can this actually be interpreted as a conformal field? Can it be a conformal primary field? And the answer is actually yes, rather surprisingly, at least for me. And for me, the path was really, think of the bosonic string, think of just three bosons, if you will. And then the conformal dimension of this thing is well known, is just the square of the momentum. So by the exact same calculation, the conformal dimension of this thing is the square of the color, but the square of the color is not a matrix anymore, it's a number. So this makes sense, but this is, of course, totally not sufficient to tell us that this is a good conformal field. It must also have a good two-point function. And indeed it does. So the two-point function is supposed to behave like the distance to some power. And this actually comes out, while it's true that these are matrices, but it's immediate that this relation comes out if you use color conservation. So in the two-point function, T2 is actually minus T1, and T1 squared is a number. And it is the number that gives the dimension of the field. Okay, this looks like a lot of other things that I don't have time to discuss. Maybe if Simon is still around, he can comment about the fact that it looks like his definition of a region. But let me just note now that if I once I've done that, then everything falls in place, right? So if I compute the correlator of these vertex operators, which are strange but actually good, then by constructions, I get exactly the result that I wanted. This result, as it must, has actually support only on gauge invariant column conserving quantities. And what else can I say? This prefactor K, which is just a normalization here, must be identified with that function K, which I called, the Regge trajectory, the average of the coupling of the cusp anomalous dimension over scales. And so we have the result. We have even, in some sense, slightly more. Because if instead of just thinking that I am in the conformal tier and I put a scale, so I just move the sphere from infinite distance, some distance in, so that it actually has a curvature. And then I go through the path integral derivation of this formula, then I see that it actually has a correction. The correction is essentially a Weil factor, and the Weil factor, of course, it's arbitrary, it's not determined by the conformal theory. But it is, in this case, it comes out proportional to the sum of the Casimir. And I would like to note that this is exactly the form that the collinear bits have, those that are still energy dependent and that I have factored out. Now I want to stop because I already spoke too much, but let me just note that automatically the non-abelian three-level soft gluon theorem comes out from the word identity of the conserved current, as was pointed out by a number of people in the audience. Of course, in this case, what I have here is a concrete realization of the conformal theorem, right? Just a set of free bosons in the Lie algebra of the group. And more interestingly, if I take the operator product expansion of two of these vertices, which again, you can basically copy from Polchinski by replacing momenta with color, then you are left with an operator which contains the sum of colors. And this is exactly what you expect from collinear factorization in the gauge theory. And then you can go and compute what is called the splitting anomalous dimension, which is also an operator, and it is known in QCD to high orders. It has this form, and almost automatically you get it. This result is perhaps not as strong as it would be, but I think that what this is telling us is that the conformal theory knows that if you take two colored particles to the collinear limit, they somehow lose the knowledge of all the other particles, and you just get an effective particle which has the sum of colors. And this is a highly non-trivial result in the gauge theory. And again, contrary to the previous page, so this the soft theorem is a three-level result, but this is actually an all-order result. Okay, so this is a discussion session, so let me just throw some questions, which I have. I put the picture of the Mars rover here because for me, studying this thing and getting these results was a bit like landing on Mars. I was truly not expecting this kind of framing of questions that I have been looking at for a long time. So let me throw a few observations again from my viewpoint. One is the fact that this factoring front is an average over scales of the cusp anomalous dimension. Now, one can simplify the correspondence a lot if one does something that a lot of people have argued for, namely that the cusp anomalous dimension should actually be used as a definition of the coupling in the non-abelian theory. And then I can reformulate the situation by saying that the factoring front is an average of the running coupling over the scale. From zero scale, which sits at infinity on the actual infinite distance, to some scale mu, which tells me I'm like shrinking the sphere. Inside the sphere is the hard scattering, outside the mu sphere is the asymptotic vision. All the dependence on the renormalization scale, on the regulator, on the coupling is all in the prefactor. And this is, from the point of view of the gauge theory, is pretty spectacular. In some sense, it is necessary in this picture because, of course, the conformal theory, it's finite. It cannot possibly know about the divergences. The divergences have to sit in front. The scale dependence has to sit in front, and that's exactly what happens However, it's a bit of a miracle that it does happen if you look at, the formula where it's coming from. Then, of course, the big question for me is that this conformal theory that we have identified is just the beginning, because it only gives me the dipole correlations. And we know that there are corrections, this delta, which later in the discussion, if you want, I can show you. So one will need to deform this theory. And the structure of delta is telling us that deformed theory should still be conformal, or at least scalable. And that's open game. What's it going to be? Do we need to make the derivatives covariant? Do we need a TT bar deformation of some sort? I don't know, but we do. Let me emphasize the last point. Once you go beyond leading order in the non-abelian case, there is an enormous amount of data which has been accumulated over the years. We know, for example, the soft current, not only at 3 level, we know it at 1 loop, we know it at 2 loops. We know the corrections to the soft factorization theorem. We know delta at 3 loops. We know what happens in the massive theory at 2 loops. And all of these data should, and hopefully can, be harnessed to constrain the extension of the celestial theory that we need in the non-abelian case. Sorry for taking too much of your time.
Thank you very much, Lorenzo. We'll defer questions to the end of the presentation session. So now let's. And Andy, are you going to use the Blackboard? Yes. Okay.
I'm gonna pin.
You are unmuted. Sorry, you're muted.
Okay. Can you hear and see? Okay.
Yes. It's a bit far away, but no.
No,
wait a second.
I don't light, yeah. So that puts him in front always.
Yeah.
Okay.
All right. So as the last person to say anything, let me thank the organizers, Andrea, Agnesi, Angelos, and Stefan for a totally fabulous conference. It's been super interesting for me, and I've learned a lot. Well, let's give a hand to the organizers. Okay, so I'm just going to ask some questions, and this subject, this field is wandering all over the place, which is good. We've engaged people studying twistors. We've engaged people studying QCD, and we don't really know where it's going. We have various goals. So I'm not going to try to give a complete comprehensive set of questions, and they're at different levels. I'm just going to throw some things out for discussion. That they're questions that I think that we can think about now and maybe make some progress on. So first question is, what are the observable symmetries of nature? So we could have, and by observable, I mean things that correspond to conservation laws, and the conservation laws can be measured. So I'm excluding redundant gauge symmetries or diffeomorphisms. So 70 years ago, the answer to this question might have been, would probably have just been energy, momentum, angular momentum, and charge. And then along came BMS. They didn't really get new conservation laws back then because they didn't understand the matching. But we now understand that there are surely infinitely many more conservation laws that we can measure, and they have observable consequences. And their consequences, of course, are various kinds, stripes of memory effects. But we don't know all the symmetries of nature. We know that these are related to soft theorems, and there are whole infinite towers of soft theorems. And so we don't know what all the symmetries are. And this is kind of an embarrassment for theorists because the experimentalists did their job. We know that we have the standard model plus GR. And so, you know, and we've known that for whatever you want to count it for, almost 50 years. And we still don't know what all the symmetries are. And even worse, there isn't even a proposal on the table for what all the symmetries are. People have talked about BMS and extended BMS. It's not clear that all of those are actually real symmetries. They don't close, and we don't know when we start trying to close them, how big it gets. This is a pressing problem, both theoretically and ultimately observationally. And there are many different ways to approach it, and we've seen them in this workshop. One of them is in terms of currents on the celestial sphere. Another one is in terms of the Hamiltonian formalism. You can also talk directly in terms of, as the amplitudes people would like to, in terms of symmetries of momentum space scattering amplitudes, and so on. And of course, all the different formalism and methods done properly should give the same answer. And I just like to say there are two big things. I don't think they're puzzles, but that we need to understand. One is this business about non-commutivity of chiral and anti-chiral symmetries. We don't know how they fit together. We've made some progress on one side, the holomorphic side, or the things associated with positive chirality, but we don't know how the left and the right fit together. And we also have worked mostly at tree level. We understand that these things have some kind of, the structure has some kind of extension to the quantum theory, but we don't understand very well what that is. And I'm hopeful that we can answer this question in a few years anyway. Okay, another thing is, what is the relationship between celestial holography and fundamental string theory? Of course, the construction was inspired by ideas from string theory. There's some hope that it might lead us back towards string theory in the constraints that it implies on scattering amplitudes. But it seems to me there are a lot of concrete things that could be done. There are only a few papers. There's a beautiful paper by, I think it was just Stieberger and Taylor, Strings on the Celestial Sphere. There have been a few comments on it here and there. We had a beautiful talk from Adamo showing in the ambitwister string, not fundamental strings, that operator product expansions on the world sheet were operator product expansions on the celestial sphere. One might hope that something like that could be true also in fundamental string theory. There also might be some connection to, there's of course, another proposal for flat space holography. It's the BFSS matrix model. And indeed, in the BFSS matrix model, there's an SU infinity symmetry, and SUN, where n is then taken to infinity. It's the size of the matrix. And long ago, it was understood that by Hoppe that the large n limit of SUN is W infinity. It's the area preserving diffeomorphisms, or it turned out to be the area preserving diffeomorphisms of the M2 brane. So there might be some other connection there between with W infinity. Another thing, not unrelated, can we find, does there exist some kind of top-down construction of a CCFT? So far, everything is, the left-hand side, the scattering amplitudes, just define the right-hand side, and we've been transforming momentum space scattering amplitudes to the celestial sphere and trying to understand, what their properties are. And but in principle, one might have, find some simple example. Maybe Shuhong was getting close to this in the very simple example, free field theory. Maybe he was getting close to this in his discussion of the generalized free field theory, what the celestial dual is. Another possibility that various people have been looking at, but been some discussions in this conference, some of us here are looking at it, is whether there could be self-dual gravity in 2,2 signature, would be a simple toy model where you might, it's so constrained, it's kind of quasi-topological theory. You might hope to directly construct the celestial dual. Also, there are interesting constructions in string theory. I'm thinking of where you start from the string world sheet and you directly construct the dual. Things like that have been done in ADS, starting with Gibeon, Kutuzov, and Seiberg many years ago for string theory on T4 cross with NS fluxes on T4 cross S3 cross ADS3, and they constructed directly the dual field theory. And also Gopakumar and Gabriel recently, in some very simple string models, were able to explicitly construct the boundary theory starting from the world sheet. Maybe something like that could be possible for flat space. In other words, if we wrote down vertex operators start out with vertex operators for space-time conformal primaries, maybe they have some interesting algebra properties. We can ferret out what the celestial dual should be. And of course, I should mention, of course, there is one very good toy model, which we've heard a few things about, which is in ADS3 CFT, you can take a large radius limit and it amounts to a Wigner contraction. And then you get, a theory in flat three-dimensional Minkowski space. And we've learned an awful lot from that. So that's a toy model that's already there. So my fourth question, which there's been a lot of discussion during the workshop, is what is a good basis for celestial conformal field theory. So we have, in the usual construction, we have all kinds of, we start out by looking for field configurations of a free field theory, which are conformal primaries. But there's a lot of those. There's the ones that you get by direct Mellon transforms. There's the ones that you get by shadowing the Mellon transforms. And then there's the ones that you get by the light transform of the Mellon transforms. And moreover, there's the conformal weight delta. So in the early stages of this subject, people were mostly considering delta equals 1 plus I lambda, and they were considering Mellon primaries. But it's not clear that that's the right thing to do. And indeed, those Mellon primaries don't close under the operator product expansion, and they don't form representations even of the Poincare group, if you strict to 1 plus I lambda. So it's not clear that, well, maybe you can that statement might not be exactly true. But but it's not clear that that's the right basis. And indeed, my own hunch is that we want to, a variety of reasons for suspecting this is that maybe we want to consider a basis where delta is in integers. Now, integers only. Now, I want to draw the analogy, I think I mentioned this earlier, with Liouville theory, many conformal field theories, they're presented in some way with a Lagrangian or something like that, and you don't know what a complete set of operators is. That's kind of what the bootstrap program has been used sometimes to determine that. You need various kinds of consistency constraints, and at the beginning, in the presentation of the conformal field theory, you might be able to write down a lot of operators, but they don't all, at the end of the day, you may not want to take all of them as constructing physical states. For example, in Liouville theory, we wouldn't say that e to the delta phi for any delta is a physical state. It lies on some line, and then sometimes in some theories, there's also some discrete set of states. So this is certainly an outstanding problem and necessary, but maybe not sufficient conditions for good basis is that the operator product expansion should close. The 4-point functions should factorize on conformal blocks. The 4-point functions of the good operators should factorize on conformal blocks associated with the good operators. And of course, they should be mutually local. Okay, so that's a very well posed problem. My fifth thing, but I'm not really going to talk about it because Lorenzo not only posed the question very beautifully, but answered half of it. So I think it's very interesting to try to understand QCD in the celestial language, both because, as Lorenzo emphasized, QCD is part of the real world, so it may help us with understanding scattering amplitudes. But I think there's another thing that he didn't mention, which is that the questions that you have to wrestle with in trying to understand how to, put QCD into this framework, like what is the celestial version of an RG flow? How do we think about that? The questions that are posed by that problem, I think, are going to be conceptually very useful in fleshing out what the idea of a celestial conformal field theory is. It's always true that it's helpful to theorists to interact with any kind of experimental activity. And that brings me to my last question, and which there was precious little discussion of. We had David Nichols, talked about it. So we've discovered some new conservation laws. They were conservation laws that were implicit in the laws of physics that we've known for 50 years, but we didn't really understand that they were there. And so conservation laws can be measured. And, of course, without the complete understanding of the structure, the prediction of the leading gravitational memory effect was made almost 50 years ago. But the more refined predictions, like the subleading memory effect, we really had to understand what the structure of infinity was. And so now there's a new prediction. And, to me, it's extremely exciting that it might be measured, okay, maybe not this decade, but the next one. So that so we're doing things that are relating to the physical universe. So, but we should, there's three things here. There's gravity. So there's the displacement memory. Well, let me just say gravity. There's the displacement memory, the spin memory, the center of mass memory. There are more memory effects, and the fact that we don't even know how to say what they're, because there's more soft theorems, and the fact that we don't even really know how to say exactly how you would measure them is an indicator of the fact that we don't really understand what we're doing yet, or what this structure is. That's a good goalpost. You've understood something new about the structure of gravity and gauge theory. What would the experiment be that would measure it, even if we can't do that experiment in principle? And of course, it's extremely exciting and even a little surprising to me that these effects aren't too small or too weak to measure. Another place, also there are experimental implications in QCD. There's a group of us showed that there's something called color memory. And of course, color is confined, so that it doesn't make it all the way to infinity. But as David explained to us, at LIGO, they can still measure displacement memory. They just have to do it fast enough. They've got this 10 Hertz window. They just have to do it before the LIGO pendula swing back into place. So you can still measure these things as long as there's a separation of scale. And so there is a separation of scale at deep inelastic scattering at this future electron, at the electron ion collider that's already funded. And so there's a proposal to measure color memory there. And, but another thing, there are also predictions for QED. And how do we measure them? Various groups, there's nothing published, but various groups involving some experimentalists have had discussions about, but finding a good experiment, but there's nothing concrete. But there might well be such a thing in the future. And let me say that these measurements, because in QED, you get, at least at the leading order, probably the biggest thing is you get phases on wave functions. And so it's kind of similar. It's not the same thing, but it's similar to Aharonov-Bohm effect, and some of the ways that you might measure it are similar to the Aharonov-Bohm effect. And the Aharonov-Bohm effect has a magnetic version, which has been experimentally confirmed, where the loop is space-like, but there's an electric version, which actually Aharonov-Bohm discussed in their very first paper, which actually has surprisingly not yet been experimentally confirmed. These experiments are hard to do because electric charge, there's a lot of noise and it's hard to maintain the coherence and suppress the background electric fields. But of course, experimentalists are getting great at maintaining quantum coherence now. So I think there's some hope that some of these things, we need a good concrete prediction for something that can actually be measured. And that means spelling out all the details of what the experiment would be. Okay, so that's it. Thank you very much.
Thanks a lot, Andy, for this excellent list of homework problems for everybody in this conference. We'll see how many of those will get done until the next conference, which I guess is in 10 days. So people get started. Okay, so now the floor is open to questions and discussions from everyone in the audience, to all of the speakers of today who are still around, and in particular, our two panelists. Maybe I'll start with a very small comment on, I guess, point 4. I guess if we want to include supersymmetry, then we need to allow for delta not being only on the integers, but half integers, right? But you imagine that
half integers, yeah.
But you imagine that we will have a basis of all. Well, I guess with the shadow discussion, we'll again have to restrict to either positive or negative, or at least start somewhere around to the left or to the right of delta equals to 1, probably, to not overcount the basis.
Right. I mean, the reason I think that the integers might be, I don't like have a demonstration that the integers are a basis, but it is true that in the scattering amplitudes, that all the terms in the effective field theory live at integer, can be in the Wilsonian effective field theory, live at integer values of the conformal weight. So by doing scattering with integer weights, you can probe all of those poles, so you can get all the terms in an expansion in the effective field theory. So that's certainly a good start. But even more than saying it's complete, because I don't know exactly what we would mean by complete. The sharp criterion for that is not clear to me. But one thing I would say is that for sure, the celestial correlators restricted to integer weights have a huge amount of non-trivial information. And they're much simpler than the generic ones. And though you might want to vary continuously to get analyticity properties, I'm not sure, but they're much simpler. So already understanding all the amplitudes with integer conformal weights is a very non-trivial problem. And if somehow that's not everything about the theory, then there would still be more to do. But
okay, there's a couple of hands that shot up. I think Atul was the first. Or if somebody has something immediately to say on the discussion, you can also just unmute yourself and jump in. Maybe that's the most efficient way. But please go ahead.
I had a question about weight, the point about weights as well. So as we've seen, there are multiple copies of SL2R groups floating around. And as you showed in your paper, that it was the SL2RW, which was, well, that's what you called it, I guess, the SL2Rs of the W2Ms. Yeah. That was the best half SL2R group to use to sort of classify the charges, at least for the soft charges. So do you think that could also act as a classification principle for all the hard boost eigenstates somehow, instead of the usual conformal group?
Well, I think there's an analogy. You know, the usual scattering is in terms of plane waves, right? We usually do plane wave scattering, and those are infinite energy states. So of course, it's, if the plane wave has a non-zero amplitude, it's infinite energy. So at the end of the day, we imagine we're going to do wave packets, but we don't actually do wave packets in the end of the day. We usually just stick with the plane waves. And so all the scattering amplitudes in momentum space, they're singular. They're either zero or infinity. Every scattering amplitude in momentum space is either zero or infinity. So of course, if you have you know, some nice wave packet, you can do a Fourier transform and you can expand it in plane waves. The integer basis, I think it's a little bit more like, if you have a function of x, you could expand it in e to the ikx, but you could also expand a nice wave packet. You could do Taylor expand it in x, just powers of x. And I think that the integer basis looks like expanding, more like expanding things powers of X. And yes, I do imagine that, and you know, I do imagine that there might be some kind of expansion, but I don't have any. But I do presume that. So the soft currents and all those things are at negative integers. I do think one will also have to include things at positive integers, which haven't been discussed very much, and those correspond to the Goldstone bosons. So yeah, I think we can learn something about. I mean, if we have using negative integers, we can get the poles of these in the 4-point function, and from those we could figure out what the what the hard scattering is.
But to get beta negative, you can also have some positive, right? You just need to have some operators that are sufficiently negative delta.
Right. I don't think we'll get away without positive beta, but we might be able to learn an awful lot from just integer.
I don't know who was next. It was either Monica or Simon. Whoever has the closest to this discussion maybe goes first.
But by order, as you can see, whoever appears first in your screen.
I see. Okay, Simon.
Well, I'd like to change topic maybe. I'm curious about developments and understanding crossing symmetry of the celestial amplitudes. They seem to have been progress in papers in the last weeks, and I know if someone could, I don't know if that would be, one could add some comments. Like in the median space, in the median basis, it definitely does not play nice because we have a bunch of discrete amplitudes that are basically unrelated to each other. But are there other basis choices where crossing is realized?
Is this a question for maybe Tom's talk on Monday, or the comments that were made by Sebastian? But I don't know if
anyone, yeah, if anyone wants to comment on crossing symmetry.
I mean, Uten gave a nice talk. If he's here, maybe.
Okay.
It's pretty late in Taiwan.
So, can you hear me?
Yeah.
Okay. So, the amplitudes, the Mellin amplitudes have problems with crossing symmetry is because they're not defined on the whole complex plane. Yes. So there are one way to extend it, we take shadows, and then I suspect that you didn't hear my talk, so I'll tell you just really very shortly. When you have shadows, then somehow this this problem with just the Mellin amplitudes being defined only on just a line, is reflected by non-single valuedness of the shadow amplitude. Now you can take a single value in a very simple way, and that leads to correlators which have full crossing symmetry and which are consistent with all known OPs. Okay, so I suggest you look into the notes.
Okay, now I will look more, but I guess I'm wondering so you have discrete data, or what's the of a crossing transformation from that perspective?
What are what?
What would be like the crossing transformation? Does it take?
Just take two-dimensional. It's like a usual, like in Bootstrap, you take S channel, two-dimensional, S channel, U channel, and T channel. And
okay. So you have a correlator that satisfies all satisfies no P in all channels.
So in all channels, and you have all this is consistent. So whatever channel you get the same length.
And this object, okay, and the point that this object is not tied to choosing particles incoming or versus outgoing, it's somehow combined them.
Yeah. Now, as far as four-dimensional amplitudes, an amplitude which is just one four-dimensional channel. which means 2 goes to 3, 4, but it can be decomposed in 2 dimensions in all possible channels. And for those, you have bootstrap. And for those, you have crossing equations.
Okay, thanks. I will more. That answered my question. Thanks.
Yeah, Monica?
Okay, so one comment on the weights. If you want to, right, so for the massless bosons, right, you need all the integer powers or the negative integer powers to get the soft theorems. And Andrea, as you pointed out, for the fermions, you need negative half integer powers, roughly speaking. But actually, I think it's a little bit more natural to just talk about left and right moving weights, because then in both cases, you need the H and H bars both need to be half integer valued, or and the half integers and the integer values. And that also makes it a little bit more clear too, that since, scattering amplitudes have this property that you can't scatter an odd number of fermions, at least you might expect then too that you're not going to find like square root powers of Z, because you're always going to get an even pair. And so and then because of these weights, it sort of works out. That's one comment. And then the second comment is, about this SL2RW. So at least in our recent work, we constructed both the currents and then also their action on massless particles or massless melon primaries. And there we actually found that the action of the W2s gave exactly the global conformal transformations. So at least in this case, it appeared that the SL2W was the same as the SL2R right. So I'm not sure whether this is a general fact, but at least in that case, that happened to be true. So there is some identification.
Hello?
Yeah, I had a question for Lorenzo actually, that I thought that there was a recent work by Lance Dixon and collaborators that a 2-loop, the soft gluon factor has a tripole contribution also. So depends on the 3 hard partons. But maybe I misunderstood. I think that the exact all order results you gave, it seemed like it only had dipole contributions. So yeah, I don't know if you could comment.
Yeah, no. So there is a tripole contribution if you have massive particles. If you have only massless particles, then the tripoles are forbidden. And actually, there are arguments that all the odd poles are forbidden. So you get dipoles to all orders, and then quadrupoles starting at 3 loops, and then you might get higher poles. But there are arguments you only get in the multipole in color expansion. You only get even.
But it's actually universal. Yeah, it's universal in the sense it only depends on the soft gluon. So it's like if you have massive external states, then in any theory it would have the same form. So is it an interesting object from this perspective to look at? I mean,
which object? You mean the tripole or? Yeah,
the two loops of gluon, the tripole contribution. Yeah.
No, these things are completely universal because they are written in a language which is representation independent. So you can put the hard particles in any representation of the gauge group, and the answer is what it is. So it is in fact universal.
Thank you.
Other questions?
If I may throw in a comment, 2.2 that was raised by Andy, and this is really far-fetched, but while we are here chatting, maybe I can raise it. I wrote in a slide that this vertex operator that performs what we need for QCD is actually, in the color kinematic sense, it is a single copy of a bosonic string vertex operator. So that's actually how I sort of saw it. So if you, in every formula that I wrote, if you replace color by kinematic, you get the bosonic string. And therefore, I mean, the bosonic string, you can think of it as a subset of some string. And that, in some sense, one might expect in the spirit of color kinematic duality, it should leak back to gravity when one would, if it was possible to understand the conformal theory on one side, maybe it would leak back on the other side that way. This is quite far-fetched, but just thought I would throw it there.
This double copy would be at the level of the factored out vertex operators. Does it work that way?
Well, color kinematic duality works that I have a certain color factor and I just replace with the color with the momentum. And if I just blindly do that, in fact, in some sense, I did the opposite. I had a conformal theory, which everybody knows, a set of 3 bosons, and they have momenta, and all I did was replace the momentum by color. And that in principle is very strange, and it's not supposed to work, but in practice, it actually works.
Sorry, Alec, you were about to say something, I think.
I was saying that to me, it looks very much like heterotic construction, because you have exactly charges on one hand, and then you are still in the soft limit. So you have no momenta, sort of the soft momenta, there are no soft momenta. So it looks like, and heterotic here exactly that what you can have correlated.
Yeah.
Is on the, so I'm not sure if it's right, as you say, double copy, but I think two-dimensional language is related to heterotic construction.
Yeah, it's also possible, yes. It's another way to see it.
Why wouldn't those in the bosonic string, why wouldn't it be a Katz-Moody vertex operator?
Well, the color one, I think, is a Katz-Moody. If I just do what I said, namely take the color and replace it by momentum, then I just get e to the I k dot phi, and that's just a bosonic string. Then I can imagine making a more complicated string, of course. And I could, as Thomas just said, I could play with that. I mean, one can, think of a string that has the color in it by some other more complicated construction. But it is just a far-fetched observation, but the kind that is food for thought. Maybe there is a way through.
Sorry, does this follow from BCJ, or is this a different?
No. This simply looks like BCJ.
Yeah, that's why I was asking.
It doesn't follow from anything.
Okay, I don't know if Simone, you unraised your hand or okay. So then Prahar.
I just had I think a bit of a technical question for Lorenzo based on his slide. So you wrote down this OPE between these e to the I t phi operators.
Yeah.
I couldn't understand the structure of that, because the e to the I t phi is a matrix operator, right?
Right.
So it has 2 indices, and then if you take the OPE, that should have 4 indices. But on the other side of the OPE, you wrote down an operator that just had 2 indices.
No. So the OPE, the object lives in 2 spaces. On the one hand, it is an operator in the Hilbert space of the conformal theory. And on the other hand, it's a matrix in color space. So as a matrix, you don't have commutation issues, because the 2 matrices T1 and T2, they sit on different points on the sphere and they commute. So they don't know about each other. So the space in which, the color space in which the object lives is the tensor product of the color spaces of each particle. And so when I do the OPE, I don't look at color at all, because the color things commute. I only look at the Hilbert space of the conformal theory, and then the calculation that I do is just the exact copy of the calculation that everybody does for 3 bosons.
Okay.
And in fact, you can take that formula and it maps 1-to-1 to a formula in Green, Schwarz, and Witten or Polchinski when they look at, as I said, you take e to the ikx1 and ik1x e to the ik2x, and you get e to the ik1 plus k2x plus sub d in terms, and it's just exactly the same thing. But it's really interesting for color because the structure that you get is what the gauge theory does for you. But to show in the gauge theory that it is that simple is an enormous effort, because what the thing is telling you is that if I have n colored particles and I take the collinear limit for 2 of them, then that collinear limit only knows, sort of forgets about all the rest of the color, and it's only, you only get T1 plus T2, and it doesn't know about the rest. Now, if you do a Feynman diagram calculation with a sufficient number of loops, say 3 loops, for example, where it has been done, you get gluons connecting every particle. And the fact that in the collinear limit you have this decoupling is extremely subtle, and it's a theorem that was proven in QCD 12 orders many years ago, but it's extremely delicate. And in some sense, if I think of the top-down approach that Andy was referring to, suppose I do take the top-down approach and I just decide, okay, there is this conformal theory with color on the celestial sphere. Let's say what it does, and I go down and I get collinear factorization. Right? This theory is in some sense predicting collinear factorization, which if I do bottom up is a very complicated thing to get. Of course, in the dipole approximation, but it's complicated enough there too.
Tom?
That's related to, I think, to Prahar question. In your talk, I was confused because you have an exponential, a sum of generators. I thought that, in soft limit or collinear limit, generator replaced by commutator. So
no, in this language, it's really sums. Of course, there will be commutators. So, for example, if I say want to derive the one-loop soft theorem, so the correction to the serious stuff begins because it has an FABC.
Yes.
And that because you start having, three gluon vertices with everybody soft.
Yeah.
And there you get commutators. And this is, in some sense, the next target in the program that I might, try to. So what I expect is that this free boson theory has corrections which have FABCs. The simplest example that I can think of is the principal chiral model. So in some sense, this is the free part of the principal chiral model. And then if I continue and I, expand the principal chiral model, I will get FABCs. And those will appear, but not at the level of the approximation that I made, which has all orders, but it is like a tower of things that are missing multiple correlations which arise at higher orders. So it's really sums. But this notation of color operators is not enormously popular outside the community, so it takes a bit of getting used.
I just wanted to add, there's also a possibility of having a WZ term.
Yes, yes, absolutely, absolutely. I think that Francisco and Hernan are looking at that. And actually, if I only had more time, I would be looking at that too. No, WCW is very interesting. It's clear that there is something in that direction. We just don't know what it is. But as I said, we have data. There is this fantastic 3-loop calculation, which has a very simple answer, which is naturally framed in the language of a conformal theory. So it's a function of conformal cross ratios, and they are exactly the ones that people have shown the last monitor. And it is a simple combination of single-valued harmonic polylogarithms that also naturally arise in a number of conformal theories. So there is something there.
Andy?
Yeah, I wonder if you could comment on the following, Lorenzo. It seems like a lot of the ideas of celestial holography have sort of been kicking around in people who study QCD for a long time. Like, and I'm not sure exactly how it's. So one thing is like in the SCET program, you have jets, and then you have this what they call the RPI symmetry. And in the RPI symmetry, I think they're changing the renormalization scale independently on every jet, right? And that's local conformal symmetry, which is sort of the basis. That sounds like local conformal symmetry, which it'd be nice to understand that in the celestial language more concretely, but it sounds like local conformal symmetry, which is sort of the starting point. And another funny thing is this phrase cusp anomalous dimension. So usually in field theory, when you say anomalous dimension, you mean the anomalous dimension under global rescalings of space-time. But this cusp anomalous dimension is anomalous dimension with respect to the boosts. It's precisely what we would call a two-dimensional anomalous dimension. So I'm sort of wondering why did they must have known, you know, why were they calling it a cusp anomalous dimension without, you know, so
okay. I mean, unless you want me to talk for a very long time, you should stop there. So, okay, question number one. Let's start with question number two, which is simpler. So, that anomalous dimension, first of all, it really is an anomalous dimension because it is the coefficient of an ultraviolet pole. So I'm just being very trivial here. So I have some correlator, it has an ultraviolet divergence. So it has an RG equation, and the coefficient of the UV pole sits, is the anomalous dimension for that RG equation. Now, the object I'm talking about is two or even one. I mean, it's a Wilson line with a cusp. So not a continuous Wilson line, but, or if you will, two Wilson lines meeting at an angle, meeting at a Minkowskian angle. So if you just have a Wilson line which draws a circle, or if you have a Wilson line with no spikes, then you just need to renormalize QCD. There are no new divergences that arise. But if you have two Wilson lines meeting at a Minkowskian angle, then there is an extra UV divergence, which is not in QCD. And to renormalize that, you compute the pole, you subtract it, and the coefficient of that pole is the anomalous dimension, and people call it the cusp anomalous dimension because of what I just said. So that's the story. Yeah, okay, no, you were freezing, you were frozen. So that's one. Now the other,
I guess if the Wilson lines are light-like, that configuration is invariant under boost. That's, I guess.
Maybe could have some comment about this because there's two things that are called custom as mentioned. There's one that depends on an angle, which is relevant for massive particles and what essentially in the time. When you take the like limit, you get some log divergence and extra divergence in the rapidity, and you get the coefficient, the number in front of that is also referred to as the custom function. And this thing that appears in the like limit is a thing that connects to this idea of local conformal symmetry.
Yes.
It's a single coefficient that controls a like limit of a cusp at a large angle, large boost angle.
Yeah. So thank you, Simon. That was exactly that was very much to the point. So coming to the conformal symmetry, I didn't have time to discuss it, of course, and maybe in 10 days in Edinburgh I will give a longer talk and I will discuss that too. But so in the game that I described, so in the QCD game, in the factorization that I described, there is a conformal symmetry. And it is really interesting that you only have it in the massless limit, and that is the reason for the fact that I had a question about the tripole. The tripole only arises in the massive case, and there is actually a very, very subtle, or moderately subtle interplay between collinear poles, which arise only when the Wilson lines are on the light cone and the infrared pole. And it is exactly this, this interplay that gives the anomalous dimension the structure that I said. So when the Wilson lines are on the light cone, you can rescale them. You can rescale all the Wilson line independently. And that is a symmetry, but that symmetry is broken when you also have collinear poles. And this dipole thing that I showed is the solution to the anomaly equation for that breaking of scale invariance of those Wilson lines. So you have the inhomogeneous solution, which has the anomaly in. That's the dipole that I wrote. And then you have the general solution of the homogeneous equation. And those are the conformal cross ratios that start at 3 loops because of other constraints. So in the game, there is a conformal symmetry, yes. Now the question why people didn't, see that they could formulate it in this way, it's a question I've been asking myself after I did this calculation. Why didn't I see this 8 years ago? Well, because I didn't, I'm sorry. No.
Okay, I would actually shortly, but maybe I can ask questions about in Lorenzo's talk there was this hard function. Like in QCD, it's standard to define this sort of finite object, and it's useful because it depends on the scale, but only through a renormalization group equation, and you can use it to predict any finite observable cross section. So there's a natural finite object that QCD people use. Nobody actually uses the variance. But on the other end, on the Selisha side, people also describe dressing of Fedif Kudish of order type. And I was wondering if someone could fill me in on the relation between the finite objects.
Was that a question to me, Simon, or in general?
Maybe you understand, yeah, but anyone who understands the question. Maybe it's a poorly worded question.
Well, I think doing something like Monica described in the non-abelian case is probably possible and probably quite intricate. I mean, the reason it is so elegant in QED is because the exponent is very simple. So you are really in a situation in which you have e to the a times e to the b is equal to the a plus b. So and it's beautiful, and that just frames the problem in a simple way. And this continues what I was trying to say a couple of days ago in another discussion session, that the coherent state in the non-abelian case is like it's been formally constructed. It has a number of nice properties, but it really doesn't know yet a lot of the things that I have used. So the fact that the soft and collinear have a special kind of behavior is something that was sort of seen in the late 80s, but people didn't push it very hard. So the existing formulation of the non-abelian coherent state, allows for nice formal things like proving that the S matrix in the coherent state basis is finite. That has been done, but the fine details of the amplitude factorization have not, to my knowledge, been formulated in a transparent way in the coherent state forms.
Okay, thanks. I will definitely watch Monica's talk. Thanks. Sorry for asking questions that have been answered in talks.
I have.
But there's one question that seemed difficult and unanswered to me in the QCD context, is that when you start defining these amplitudes that are finite, unitarity becomes messy, right? To actually calculate probabilities, cross sections, there's a whole the combinatorics of doing. You have to subtract things in your real emission contribution. The systematics of these nested subtractions is very intricate. And from a bootstrap perspective, we lose control over like the sign. It's usually great that m dagger m is positive quantity, and we kind of lose that for these finite quantities. I wonder if this approach gives control over the sign. It's nice to have a unitary formula, but like the sign matters.
No, I agree with the existence of the problem. Although unitarity is very useful in the context of, the divergences themselves, because a lot of cancellations can be explained with unitarity between, between different cuts.
Exactly. It's nice to see that divergence cancels, but I care about the sign of what's there.
No, exactly. I agree with you. If you want to do, to work as you do on unitarity and crossing and causality at the level of the amplitude, this infrared factorization may split things in a way which is not nice. I don't know.
So Lorenzo, maybe just to follow up on that, I mean, if you use hard-soft collinear factorization and define the hardest matrix like how Schwartz defines, then it has the other problem that there is an extra UV scale dependence that comes in the hardest matrix. So is that related to what you are saying? These new problems that may crop in? I mean, you cancel infra divergences, but you may get new UV divergences in the.
Yeah. Well, yes, but it's not that so much that worries me. I mean, I think that the definition that Schwartz and Feige give for the S matrix is totally okay, and I think it could be mapped to earlier work by Marchesini in the 90s. But it is very formal in the sense that you have an object that it is finite, but the only way that you can actually corner it down and compute it is by adding and subtracting and order by order, and there is some information which is not easy, not sort of transparently encoded in that expression. There is this object, we know it is finite. Yes. But we cannot write it in a really nice way as we might like to. Let me put it that way, at least to my understanding.
I see. But is it correct to say that compared to the earlier, like the dressed states formalism, I mean, with this Schwartz S matrix, you can at least do computations to say like some lower loop order. I mean, at least that's, I mean, I thought that was one of the things that you could do with the S matrix. But except that there was extra UV scale dependence.
Yeah. No, but look, if we had Stefano Catani in the audience, he would probably tell you that he has been doing two-loop calculations with coherent states since then. Stefano, unfortunately, is the kind of guy that doesn't really write down very explicitly the calculations that he does. But either so long as you stay at finite order, either formalism can be expanded, and when you expand, you have full control because everything is perfectly well defined.
I see.
But some things that happen to all orders are not so easily seen in the coherent state basis, and many years of work in the factorization framework or in the SCED framework, they are really equivalent. Of course, they have shown some detailed structure that is not easy to see in the coherent state formats.
Thanks.
Or maybe somebody can. Maybe it's my fault.
Tom?
I have just, again, very quick question to Lorenzo. When I was a student, perturbative QCD was just starting, and then there was always issue whether Bloch-Nordzig, like Kinoshita-Naumberg, are valid for a non-Abelian case. Is it settled now?
So, okay, this is the moment for the. I lost your audio.
Yeah, and maybe can you repeat the question because the sound wasn't great. So
the last sentence was lost.
Oh, I was mentioning the whole question or the last thing.
I only missed that.
I was just asking about status of the proof, whether there's a rigorous proof on non-Abelian Bloch-Nordzig and Kinoshita-Naumberg.
Yeah. Okay, so this is the moment for the advertising break. So let me take the advertising break. I am just finishing together with my friends and collaborators the physics reports, which will contain all the answers to these questions. I hope it will be out soon. But to briefly, yes. So we understand what's going on. So Bloch-Nordzig doesn't work. This has been known for a long time. Bloch-Nordzig meaning cancellation only when you sum over final states. And KLN always works. KLN always works, but it's not very useful in QCD because we don't have control over the initial states. So KLN would tell you have to sum over the degenerate initial states, and at LHC we get a proton, and we don't know the relative weight of the wave function with one quark or with a quark and two gluons and so on and so forth. So we have to do something else. So KLN is quantum mechanics. KLN always works, but we have to use something else.
But Bloch-Nortzik, what did you say? Bloch-Nortzik holds or no?
Bloch-Nortzik fails in the non-abelian case, but fails in a controlled way. So if you look at a process like Drelian, for example, the failure of Bloch-Nortzik is suppressed by powers of the hard scale. So it causes divergences, which in front they have like lambda QCD over Q squared. There is actually a recent paper that revisits that whole issue by Kirill Melnikov and Kaula and Melnikov. They have redone exactly that calculation that was done, way back then, 40 years ago, but they have redone it in modern language with dimensional regularization, and it's beautifully clear. So no Bloch-Nortzik, but it fails in a controlled way, so we can still make predictions at the LHC. It could have gone differently. It would have been pretty catastrophic.
Maybe to discuss a bit about the second, or is it the third? No, the second question on Andy's list about the relation with the fundamental string. So I had already some discussion on Tuesday, I think, where this beautiful result of Tomasz and Stefan was brought up, where the worldsheet of the string gets pinned to the celestial sphere in some large, taking the conformal weights large. And then we had some discussion about higher dimensions. And so I would like to raise the question, do we really, what is the evidence that the worldsheet of the string should be identified with the celestial sphere in generality, not just in the 4D, 2D situation? Maybe someone has some thoughts on this.
I mean, so the idea is that you have the string worldsheet on which the vertex operators of, for example, the gluons are touched. And then when you consider this large conformal weight limit or this high energy limit in string theory, you do a subtle point approximation, and then you need to compute the subtle points which give you the points on the worldsheet where this action is maximized, and these points are given in terms of kinematic invariance, which in turn then you can translate into points on the celestial sphere. So I think a priori, that's also what I think was the conclusion on Wednesdays. A priori, there's no obstruction that this also holds for for any endpoint amplitude in string theory. But of course, interpretation, so this is only a coincidence of string theory and celestials, I mean, string worldsheet and celestial sphere in this large lambda limit. So of course, in that case, you might expect some free field theory at this point, but it's not clear what's the relation between strings and celestial spheres away from this limit.
Right, and then also the question of, is this happening? Is this, I mean, so the computation that you did is in 4D, 2D, and we don't really know what happens in high dimensional celestial holography. Or maybe I should ask Andy what you had in mind when raising this question. It was related to that, or you had something else in mind here?
So yeah, so of course, the string world sheet couldn't be the celestial sphere in more than 4 dimensions. But I wouldn't dismiss the connection on that basis. You know, one of the lessons from string theory, or at least one I learned, I spent many years in the wilderness trying to understand string duality in 10 dimensions. And that's the hard place to understand it. It's weirdly easier with the original breakthroughs, Ashok's work on computing the spectrum of dyons and n equals 4 and so on and so forth, it was in 4 dimensions. And one of the things about string theory is very different. The structure of the dualities, this is very different. If you look at the BFSS matrix model, that it has some generalization. It starts out in 11 dimensions, it's 10, it goes down to 8, and then it breaks down and becomes useless and strongly coupled. So different dimensions are different. I don't know, but it seems to me to be too much to say that, we're saying that there's some kind of celestial conformal field theory that computes whose correlators are the space-time S matrix. And we know that that's true in some sense in tree level and string theory. Now the map is a little different, but it seems hard to believe that these could be completely, that you would have 2 conformal field theories which are unrelated, which both compute the S matrix. Now, one of the things that's funny is, of course, in string theory, you sum over different genus, and the celestial sphere always has genus 1. Well, in 2-2 signature, I guess it has genus 0. 2-2 signature, I guess it has genus 1. It becomes a torus. But interestingly, Gopakumar and Gabriel had that problem, right? So they related they sort of did this thing from the string world sheet to the dual 2-dimensional conformal field theory. And they constructed it explicitly. And you might wonder what happened to the sum over genus. Well, there's CFT2 on the boundary had twisted sectors, and these twisted sectors became branch coverings of the sphere, and which was why I was so interested in the branch coverings that Adamo was talking about, and that the ambitwister that people like to talk about in the CHY string and in the scattering equations, and then okay, so branch coverings of the sphere are higher genus surfaces. They don't cover the whole moduli space of higher genus surfaces, but Gopakumar and Gabriel miraculously found that the contributions to the scattering amplitudes localized on the submanifold of moduli space that corresponded to branch coverings. So there was some long story, a very complex and intricate story, which made it all work out. And I'm hoping there's something like that in fundamental string theory, but I can't be any more explicit than that.
It's the homework from the workshop, I guess. Okay, so Alok, I think, was next.
Yeah, I had a question for Ashok, just following up on this. So Ashok, what's the understanding of infrared divergences in a superstring amplitude? And I mean, are there some infrared Redshift observables that we understand using string field theory or something? I mean, Prahar raised this question also yesterday, I think, in the discussion, but I don't know. I think Ashok was not there. I don't know if Ashok is there, maybe he can.
Yeah, I'm here. I mean, I think the infrared behavior in string theory is exactly the same as in quantum field theories. because yeah, it's only in ultraviolet that they differ.
So are there some, like as Simon was saying, some infrared safe observables that in QCD we can define? Is there some understanding of in the string theory, like what are the infrared safe quantities that?
Yeah, for example, inclusive cross section will be infrared safe, right? That's the simplest example.
I see. And beyond that, is there anything?
Yeah, I mean, whatever you can do in quantum field theory is the same in string field.
I see. Okay,
yeah,
okay.
Because the infrared behavior, I mean, string theory is like quantum field theory.
But something, this divergences you should be able to see from moduli space, some behavior in the
yeah. So you see the divergence exactly in the same place in the moduli space where you see the divergences in quantum field theory. That if you take the quantum field theory and rewrite in the Strominger parameterization, right?
I see.
Then the divergences are, you can see where they are in the Strominger parameters.
I see.
Yeah. And those Strominger parameters become the moduli of the Riemann surfaces.
Okay.
Do we have a clear idea of what a soft particle is? Zero momentum, as far as in string theory?
Yeah, I mean, it's the same. I mean, soft graviton, for example, right? String theory has a graviton, so you have the zero momentum gravitons, right? I mean, are you asking where they come in the Riemann surface? I mean, is that?
Well, I guess some of them are related to pure gauge excitation, so they might go to the boundary, or
I think it's no different from what you have in normal quantum field theory.
I mean, at the level of scattering amplitudes, I think I agree with Ashok. I mean, you write the string scattering amplitude, and it has a representation, which of course has a moduli space. It has some integrals that you have to do, but the momenta in that expression are explicit, and you can take soft limits exactly in the way in which you would take them in quantum field theory. Then, of course, there you have alpha prime, you have a scale, and you have to decide what to do about that. But
but that's UV. I mean, alpha prime basically controls the UV.
I agree.
Of course, whatever you can do, as Ashok was saying, whatever you can do in field theory, you can do in string theory. But maybe string theory gives us some extra insight or some new way of understanding it. I mean, if we were just looking at these vertex, if we were just, the usual thing would be, if you look at, the usual statement would be that vertex operators which create pure diffeomorphisms are total derivatives on the world sheet, and so we can throw them away. But we know that that's not always true for the soft particles. So what there might be some, there might be some interesting way. How do we understand the memory effect from the point of view of the world sheet? There might be some interesting way of.
Well, okay, soft theorem you can certainly understand from the world sheet, right? As in terms of, because soft theorem is a scattering amplitude property, right?
Yeah.
And that you can certainly see in the string world sheet. I mean, you're asking how do you see?
Are you doing anything more than taking the field theory limit and then?
Yeah, you can. I mean, if you look at the scattering amplitude, you can explicitly verify that the scattering amplitudes do satisfy soft theorem. Because you can write the scattering amplitude in terms of gamma functions, for example. Take the 4 graviton amplitude, right? You write them in terms of gamma function, and then you can take the soft limit of one of the gravitons.
I guess I'm thinking about some conservation laws we can understand in string theory in terms of deforming holomorphic contour operators around the world sheet and having and that gives us some word identity that we can understand in a very, let me put it this way. We now understand all the soft theorems in terms of celestial conformal field theory, in terms of deforming contours of integrals of holomorphic operators. And I guess there's a question of, can we understand them also in terms of deforming contours of holomorphic operators on the world sheet? That would be a start towards understanding the relationship between,
Yeah, so typically what happens is in string theory, you see these kinds of abstractions, I mean, things which are supposed to, naively supposed to give zero answer because it's total, if it's pure gauge, but it's actually not pure gauge, is that you get integrals about the moduli space which are total derivatives, but the boundary terms are non-zero.
Yeah.
So you can look at the boundary terms. So it's like abstraction to integrating total derivatives because they are non-zero boundary terms. Yeah, so I presume you can probably see the soft theorem also that it's almost decoupled, but not quite because it's there are boundary terms left over.
And there's other interesting parallels, so this fact that right, that global symmetries become current algebras on the boundary. Or gauge symmetries become current algebras on the boundary, and they also become current algebras on the world sheet.
That's right, yeah.
So far, it makes you think that the boundary is the world sheet.
I agree, yeah.
and there's also the fact, if something like Adamo said, if something like that can be derived in string theory, that the world sheet OPE is also the celestial OPE, then if we have then if we do the factorization on conformal blocks, we could do it on the world sheet, or we could do it in the space-time, and it all comes from the OPE. It should be the same thing. Well, even the more basic answer is, one of the things, if the 4-point function in celestial conformal field theory, compute it in the bulk, you have S plus T plus U. But if we look at it on the celestial sphere, we can decompose it in a conformal block expansion, the S channel, the T channel, or the U channel, not the sum of them, right? S or T or U. So somehow by going from the bulk to the boundary, we went from S plus T plus U to S or T or U. Now, S or T or U, of course, is the origin of fundamental string theory. Veneziano tried to write down an amplitude that you could sum over S channel or T channel or U channel, and you would get the same answer. And now we know that that's true in any quantum theory of gravity, but we don't have a lot of control over it. So a lot of arrows pointing in the direction of a more concrete connection, but but also a lot of things that are not the same.
Yeah. I guess one thing which is not so clear is the world sheet. I mean, the Vertex operators has all the massive states also.
The what?
In the string world sheet, the Vertex operators include all the massive states also.
Yeah.
Not just the massless states.
Yeah.
So that's one thing one probably has to understand from the celestial CFT viewpoint.
No, it's also true that in the celestial CFT that the massive states are computed in the OPE algebra. So if you take, this is an interesting thing, right? In an energy basis, you can never, momentum conservation prevents you from sort of two collinear photons from producing a massive scalar. But in there's no obstruction to it. And indeed, there have been some explicit computations now, I guess. But we know, for example, if we have a 3-point coupling between two, in fact, Monica and Mina worked a lot of this out in their recent paper. If you have some massless spinning states and their OPE will create a massive particle. So if you have collinear particles in boost eigenstates, if they're massless, they can make a massive one. And that would be true for string states too.
Yeah, but somehow that information has to go in, right? The massive state spectrum. Suppose you are doing it in pure gravity.
Yeah.
I mean, that will not have massive states. So that information has to go in somewhere.
Well, I guess we think pure gravity doesn't exist.
Yeah.
Or maybe it does. It would be nice to prove that.
Yeah. So can one see from celestial CFT OPs that you necessarily have to include massive states?
Yeah. Well, and in fact, in our, yeah, you can see that. And in fact, when we did an analysis of the conformal block expansion of massless phi to the fourth with a contact interaction. And it looked like a conformal block expansion had intermediate massive states. It was a limit, a kind of limit of the massive exchange OPE. So massive exchange 4-point function. So of course, strictly speaking, in phi to the fourth at tree level, the celestial amplitude is not defined because the Mellin transform is only marginally convergent. So you have to regulate it. And the regulator that you use is more or less equivalent to turning it into a massive exchange. But then in Mellin space, there's no scale. So so the massive states don't decouple. Once you sneak them in as the regulator, you can't get rid of them. So yeah.
Tom had his hand up for a while, I think. You're muted, Tom.
Going back to end this, point 2, yes, which was possible connection of CCFT and strings. There's actually another theory which you, okay, that's possible. You also often mention another theory, which is UV. And I think that there is some connection, there must be some connection between CCFT and UV theory. The correlators that we get an integral representation have the form of Cobb-Nielsen, but with in the simplest case, there is one extra point. So they do not look, and that point look like the insertion of charge screening operators in the minimal models. And, but that is only in the special case of the soft shadow. So in general, you will have these correlators look like, I think, there is a similarity between those correlators and correlators which you'll get in UV theory. So I think there may be some interesting relation with between CCFT and UV theory.
On the gauge theory side, you could say that the background charge in the conformal theory is 0 by the color conservation. So
no. This is two-dimensional. I'm talking about two-dimensional CFTs, in which the minimal model.
No, I'm sitting on the sphere. I have a conformal theory. On the gauge theory side, the background charge is 0. so, you know, insofar as we have it. But I agree with you that it would be interesting to look at the background charge non-zero. So that leads to a number of possible generalizations. Just saying, no, just what I have now is like it is a theory with zero background charge. By the way, if I can interject a very small comment, it just occurred to me that the first person to prove a factorization theorem like the one that I was discussing was actually Ashoke, and it was exactly 40 years ago. So I thought it was worth mentioning. So congratulations, Ashoke.
Thanks. Thanks.
Atul?
Yeah, just about the soft theorems discussion in string theory. Is there any, do you guys have any speculations for what the W infinity symmetry might get deformed to if you study the soft theorems of stringy graviton amplitudes? At least the MHB, stringy graviton amplitudes. Could you find capital W1, like a concrete example of capital W1 plus infinity in stringy soft theorems?
Well, let me just mention that, right, once you are dealing with the stringy amplitudes, now you have the correction, the EFT corrections to the W infinity, and I'm not really sure how those are supposed to work. We basically assume those are absent. So like the higher, basically the W infinity, right, comes from like minimal coupling of gluons or minimal coupling of gravitons, but no curvature corrections.
I'll make an additional interesting observation that, so we know that superrotations are very difficult to define in higher dimensions, or because it's very unclear how to construct the phase space. But I think some preliminary results on some work that I'm doing, actually, this is before I knew about the W infinity, was that there's one way to make the phase space well defined is to work with area preserving diffeomorphisms in higher dimensions. Instead of, so generalizing the global conformal group to all area preserving groups as well. So that perhaps suggests that that's perhaps the higher dimensional generalization of this W infinity algebra.
What is the surface you're preserving the area of?
Oh, the sphere.
It is some auxiliary.
Yeah.
Yeah.
I mean, the D-dimensional sphere. So bulk is D plus 2 dimensional, and I'm on a D-dimensional sphere.
Oh, so you have some D-dimensional generalization of symplectic diffeomorphisms.
Yeah.
Okay.
Wait, this is a question for you, Atul. What the W infinity is well known in the twistor world. It's not exactly the celestial sphere it preserves, right? It's some light transform of the celestial sphere, or
that's what I suspect now. But yeah, that somehow the celestial sphere opens up into this mu alpha dot plane. So you remember the spinor helicity coordinate lambda twiddle alpha dot or lambda bar alpha dot, whatever you call it. You have Fourier transform in that, and it's that two plane, that's Fourier dual to the two plane of lambda tilde alpha dot. So some kind of Fourier dual of the celestial sphere, but I need to make it precise in terms of some charges acting on some operators living on these planes in some representation. I think you were also asking Hongliang Zhang if this was like a known representation. I don't know if there's a good answer to that, if anyone found an answer to that.
This isn't like in Witter twistor string. That's what you do. You do just from lambda tilde, and then you transform it out.
Yeah, that was the idea. You take lambda tilde and you transform it to some mu alpha dot. And then these are the two plane of mu alpha dots is the two plane on which the W infinity symmetries act in the canonical way as Poisson diffeomorphisms.
So the Penrose transform, you say, is like shadow. You are saying that Penrose transform is saying of a shadow, or I'm confused.
Yeah. So okay, this is not the Penrose transform. Just to avoid confusion, this is like a half Fourier transform, which is like a dual to the Penrose transform. But yeah, I'm saying that this Witten's the thing that Witten did in his paper, this half Fourier transform, seems to be the same thing as the light transform. It's actually a linear combination of two light transformed states, but it's like just a two-term combination. But it seems that it's giving the same object. So my suspicion is that if I compute a correlation function of just light transformed operators, and then insert a light transformed soft particle in that, then the representation in which that soft particle will act on all the light transformed primaries will be some kind of a canonical diffeomorphism generator action on these light transformed operators.
So how is momentum conservation realized in this case? How in twistor space once you do that operation?
It's one of the W generators. It's W3 halves.
Yeah, this is momentum conservation, just lambda alpha, lambda tilde. So your Fourier transform, so that just becomes lambda alpha d by d mu alpha, right? This is one of the, becomes a linear generator. But I think in this is similar to what I think Anna showed for the shadow, for the light transform momentum generators as well. I don't know if you, something similar, lambda d by d mu. I think in your case you had z d by d z bar, some generators like that. When you write the momentum generators in the light transform basis.
Yeah. Yeah, in fact, we found those expressions I showed using, I
listened to your talk at somewhere else.
I think it's related to the twistor transform, but anyways, I will talk more about that next week. Yeah, but the expressions I wrote down, they're found via like a very simple kind of like argument. It doesn't use twistors, but I think they're related. Yeah. I think they're essentially, yeah.
Yeah, this was in your talk. I listened to another one of your talks. Maybe I'm remembering that one, like a few weeks ago. But yeah.
Francisco?
Thank you, Andrea. I have a question probably for Thomas or Stefan. Do you expect that this pinning of the worldsheet onto the celestial sphere in the large conformal dimensional, on the conformal dimensional limit, do you expect that to hold also at the loop level? I wonder because of the topologies now, essentially what Andy said also, that now you have different topologies, you have torses, or for open strings, you have disks with holes. Then it's not very clear to me how that will work out.
I mean, it's also not clear to me either. I mean, what is true, of course, when you do this Gross-Mendel subtle point approximation, that doesn't change so much when you go to loop level. I mean, it's again a subtle point approximation on the Riemann sphere of genus G, but I mean, then you have elliptic functions, so the subtle points are probably given by some ratios of elliptic functions, and that needs to be seen how this is mapped to points on the celestial sphere. So maybe it's a little, I mean, that's just maybe a crazy speculation. Maybe it's like a mirror map you have on Calabi-House, that there's some modular function in between when associating the subtle points to the points on the celestial sphere. But I don't know, I mean, because, I mean, simply because also we don't have much results on the celestial spheres for one loop amplitudes.
Does anyone know if it's true for the higher solutions of the scattering equations in the CHY string or the ambitwister string?
It should be, I think we had this discussion last time on Tuesday as well, but it should be true at least for MHV amplitudes. Beyond that, it's not clear. Or it's, I don't know about taking the large lambda limit, in which case it might hold more generally.
But is it more about loop corrections for scatter? What is the state of scattering equations for loop corrections? We have something similar. That may be more related to the question. So
there are one loop scattering equations, and I think two loop as well. But they contain dependence on some global one form. I mean, some global data on this torus. They're not simple scattering equations like on the sphere. They contain some extra one forms in the scattering equations that come with the loop moment, that sort of encode the loop momentum integrals. So yeah, it's not clear. Maybe Lionel can make a comment on that. He knows that better.
Sorry. No, but it bumps up the degree though. You get more points and more singularities. So having higher loops, I think Yvonne and Ricardo Yvonne and two Ricardos have now got it running at 3 loops, and but each loop order just increased the degree of the map. So
if you do the nodal Riemann sphere construction, then you just get a sphere with extra points, right, Lionel? You could still think of it as
but I guess there's also a version with higher genus as well, so that would probably be some, but they're all covers, I guess, of the Riemann sphere by the, they're all pinned, I guess. Function.
Again, maybe a good place to check this pinning explicitly might be the self-dual case and n equals 2 strings, where you explicitly have something in 4 dimensions and 2 signature, and which only works for the self-dual sector, where the MHV, for which this isomorphism between the celestial sphere and the world sheet is most precise. So another reason to study self-dual CCFT, I guess.
Cool, thanks.
But I guess for the true, sorry.
Go ahead.
I was just going to make the remark that for the true string, though, surely in general, you wouldn't expect any canonical map between the world sheets and the celestial sphere. I mean, you'd expect it to be some random thing with some moduli that you'd be integrating over. In the case of CHY, it's a discrete sum, but it's still you branch cover or something. But in the true string, it would be there'd be continuous moduli that you have to integrate over.
I mean, it's probably some function, modular function, depending on the moduli, which is supposed to be described or mapped to the points of the celestial sphere.
And it would be a continuous set of moduli that you'd have to integrate over. I mean, you wouldn't really necessarily expect it to be holomorphic, though.
Still, you might hope that maybe some sort of Gabor-Kumar mechanism might work for the true string.
Well, yeah, perhaps. Sorry, I was interrupted, Andrea.
No, I was just asking for if there are more questions or comments, and you did exactly that, so thanks.
I'm sorry, okay.
Anyone else? Maybe have a quick question to Alok and Praha if they're still around. So, are you around? Yeah,
yeah, I'm
so
around.
On Wednesday, Henrietta told us about this derivative corrections and effective field theory corrections to the sub-leading soft theorem in QED or for photons, and the sub-leading soft theorem in gravity. And I think you guys had some work on how this translates to in the asymptotic symmetry analysis. I think for the photon case, was just going to ask what the punchline there was again, and whether the gravity case has been looked at.
Yeah, yeah. If Praha is around, maybe I will let him answer. Is it,
no, you want.
Well, okay, yeah. I mean, we didn't do gravity. We don't only the QED case, and the punchline was that the asymptotic symmetry is the same, but the charges are modified, because the charges depend on the 1/r cube mode of the field strength. So the equations of motion change at that order because you are adding higher derivative operators, and so that changes the functional form of the charges, which precisely produce the modified soft photon theorem. We didn't do gravity, but I think it should. I mean, we expected that it would go probably the same way. And Praha, you want to add something?
No, I think you got it all. Yeah. Yeah, it's simply because the subleading soft theorem is you have to do a divergent gauge transformation for that. So you have an extra power of r in the gauge parameter, and you're essentially, because of that exact factor, allowed to add an extra power of 1/r in your Lagrangian, so that those two factors completely cancel and you get this extra contribution to the charge. And that's exactly what happens when you add higher derivative terms. But only a small subset, because you can only add terms that contribute an extra factor of 1/r. Anything that goes beyond that will not contribute to the subleading soft theorem. And the precise list of operators which were given by Henrietta were the exact operators that give you 1/r.
And for gravity, it's just a technical, more difficult to address, or was there another reason why you didn't?
No, just technically more difficult, just extra indices, which we didn't want to deal with.
Monica?
Yeah, I had a follow-up on that. Do you guys know of, maybe a clever way to design a memory experiment that would be sensitive to, right, like the effective field theory couplings that appear in this corrected symmetry transformation?
So the memory, I mean, but do we know what is the memory for the subleadings of graviton theorem? I mean, even without any correction, I don't know if there is any memory interpretation for that.
Well, there's at least, right, the work of like Sabrina and Slava and Andy for that's
the spin memory.
Right.
So that's universal though. I mean, that doesn't get to it.
Right, but.
Well, there's let's see. So so nobody's published a paper on measuring the subleading soft photon associated memory effect. But Ray Weiss came up with a proposal which he thought was for the leading memory effect, but it was when he wanted to use neutron interferometry. Neutron interferometry is insanely accurate. They can measure now, they can take two neutrons and split them and measure the change in the wave function due to the interference, due to the change in the gravitational potential. and the reason it's much easier to do interferometry with neutrons than with electrons, because once you have a free electron, it's got charge, it wants to go to conduct, but neutrons kind of mind their own business. But neutrons have dipole moments. And so I think this interference would be really more properly thought of as having something to do with the subleading. This isn't an answer to your question, but it's maybe a direction for an answer. This interference probably has something to do with, it's probably more properly thought of as having something to do with the subleading soft photon, subleading soft gauge symmetry. And I guess, but then you need, for corrections, you need a massless scalar.
No, you also, gravity corrects that one.
Oh, okay, yeah, great, right. So maybe, I mean, they're measuring gravitational effects with neutrons. So maybe there's an interesting memory effect there that could be measured. That would be amazing.
One thing over there, one thing about these corrections is that they actually change the type of external particle. I don't know how that goes into this with the memory. How will that affect this whole memory experiment? So in other words, a photon couples to the graviton and then converts it into a photon. That's what this higher derivative coupling does.
Yeah.
Yeah.
Actually, I guess I don't even really fully understand, haven't worked out what subleading memory, nobody's worked that out. Before you talk about corrections to it, what's the leading thing?
Do you expect there to be a memory effect? Like, there's no global symmetry associated to this.
Yeah, exactly. Yeah.
Soft theorem. I always had some, I mean, this is some, I don't know where it's coming from. I always just felt, if you have some global symmetry associated to it, then you might have some memory effect, but there's no such thing for the subleading soft photon.
Yeah, that's a great question. Yeah, that's a great question. I'm not sure. I don't know the answer to that. There's a Goldstone boson.
True.
And the Goldstone boson shifts. So
I suppose the claim is that the Goldstone boson will not have a zero mode because there's no global symmetry, but perhaps locally, which is what memory will measure. Locally, there could be some conservation. I mean, there are conservation laws, of course, locally.
Yeah, now that you say that, it makes me realize what an interesting question it is. And probably the easiest one is the subleading one in QED.
Yeah. That also couples to fermions. I don't know if you could use, actually the fermion coupling is easier. It's basically the first n equal to one, n equal to 1 dimension 5 operator that you get. That would be easier, makes a bit more sense. It doesn't change particle type, it just takes fermion to fermion and just couple.
Right, and it's sometimes called Lowe's magnetic dipole theorem. Right, so that's much better than f² phi. Right.
So,
Sidebar.
yeah. So sorry, just one thing I can say maybe to Monica's question also is that, I mean, we can understand all these conservation laws in terms of charges at the sphere at the U equal to minus infinity or V equal to plus infinity. So the subleadings of photon theorem comes from the multiple moment, which goes as 1 by r cube, the FUR, I mean 1 by r cube mode of the FUR. So I don't know, maybe that's what one is measuring when, I mean, I don't know the experiment, what one is doing, but like that's what we would like to measure, right? I mean, and that identification is independent of whether we add a correction or not to the Lagrangian. So it's always this 1 by r cube component of FUR that is conserved. And when we write it in terms of the data at scry, its functional form will change if the Lagrangian has the specific higher derivative operators. So I don't know if that answers, Monica, I mean, partially answers the question.
One thing I was confused about was that I thought, at least in a leading case, you can think of the things that are detectors of the memory effect are like charged under the symmetry. And so you can think of removing it by acting with the symmetry. But now we know, at least at this particle level, right, these subleading symmetries in the presence of effective field theory, so I understand this is making it more complicated, but like they change a particle type. Or at least in the fermionic case, like maybe they don't change the particle type, but they do flip the helicity, right?
Mm-hmm. Yeah.
So does that occur in the memory effect? Like is that part of the story or is it not? And I'm not sure what the answer is.
Yeah.
Well, I think it has to be, but I think we have to understand what the leading term is before we understand that.
Yes. Maybe I can follow up, Andrea, and ask one question to Ashok if Ashok is still there.
I'm still here.
Yeah. So Ashok, in your proof with Vishwajit and Arnab, when you derive the classical logs of theorem, I mean, is there any way that we can also derive the spin memory term, at least for some specific cases? I mean, the reason I'm asking is that, all this work which has been done by Nichols and Tucholsky, etc., when they are kind of trying to rigorously derive the spin memory for, say, in spiral. But naively, we would expect that if there is this log, then the spin memory term will be ambiguous, right? I mean, there will be no universal answer to the spin memory, right? But does your proof tell that for some specific cases, you could have a spin memory, which you could, still predict? It's not a very precise, I don't know if I make it.
Yeah, I think if you think of it as a power expansion, series expansion in Newton's constant, then maybe you can isolate the spin memory because this log correction has one extra power of Newton's constant.
Yeah. That's why I'm asking. So you're saying at 1 p.m. if we do that thing, then it will only have the spin memory. We will not have Yeah. But the recent works of Tucholsky, etc., they go beyond that. So that was the point that you go to higher order PM expansion, and so then there should be a mixing, right?
Yeah, then there will be a mixing, I would think.
But is there some like maybe for some systems like in spiral phase or something? I mean, naively the tail comes asymptotically, right? We have to wait very long to see the tail. But is there some way that if you are only looking at the waveform from the in-spiral phase, maybe there is a way to, distill the spin memory part? I mean, I don't know, I'm not being very precise about it, but is there what do you think? I mean, is there an observable we could define for some systems which is spin memory?
Even beyond lowest order in the
beyond, exactly, beyond lowest order.
Yeah, it may be possible. The point is the soft theorem by itself doesn't tell you how long you have to wait, right? It just gives the late time behavior. But I think this kind of classical analysis, of course, will tell you what the full response is.
Yes.
Right? I want us to look and see, what one gets. Yeah, it's not impossible.
But the log is defined only up to some, I mean, it's log omega by omega, some reference frequency. So it's always defined up to some order omega to the 0 term, right? So somehow.
Yeah, but in principle, you can calculate it. I mean, because you are doing iterative solution.
Right. Okay, okay.
But, okay, you can calculate it provided you know the finite system. No? But as long as you don't know anything about what kind of interactions are taking place,
yes,
you cannot calculate it. But once you know the full dynamics,
yes,
then in principle the constant piece you can calculate.
So it's not, yeah, so it's not a theorem. You're saying it won't be a theorem, but of course, case by case, we can compute it.
That's right, yeah.
Okay,
yeah.
okay.
It may not be universal.
Okay.
So while we're talking about memory, maybe I'll also ask about memory associated to fermionic soft theorems. Does anyone have any idea how those would be? Would there be such a memory? What would they look like? The soft Fortino theorem, for example.
Yeah. I mean, the fermions are not classical objects, right? So I think it will be.
Yeah, exactly.
Yeah. So it will be very hard to interpret this as some classical shift.
Right.
But of course, there's quantum effects, right? That one can certainly study.
Yeah.
And they're all particle changing, right? That's how they act.
Yeah.
Yeah, the fermion. Oh, yeah, they have to be. Fermion has been half, so it has to.
Fortino certainly
goes on to fermions.
Yeah. Yeah, my feeling is that the particle changing processes probably will not have classical interpretation in the memory effects are.
But you think even those without global symmetries will, so for instance, many of your log omega soft theorems, they're not associated to any new global symmetries. But you
at least not that you know of. I mean, maybe Alok and Miguel will find something, but yeah, right now they don't. I mean, the connection seems to be unclear.
No, I mean global symmetries. There might definitely be some new local asymptotic symmetries associated to it, but like.
Yeah, but they are certainly observable, right? The log omega, when you translate to late time behavior, in principle, you can observe them.
Right.
Also, I think that the usual displacement memory, the thing we measure, isn't a global symmetry, right? It's the relative displacement, right? It's not a global time translation. It's the relative displacement between two nearby objects.
Yeah, the memory effect does only measure the local.
Yeah.
Yeah. So.
Any more comments? We can see if we can set the record today. I think we have the record.
Andrea, did you ever figure out if your celestial diamonds might also somehow, if these light transform states might also somehow fit in your celestial diamonds?
Yeah, I mean, they probably fit. I mean, there's, yeah. I mean, the shadow relates the left and the right, right?
Can you make celestial polytopes now?
Well, we have already the pyramids, right, from supersymmetry.
Exactly.
So we'll see what kind of structures we can. Yeah, I mean. But yeah, since you can take these transforms, you can see what kind of connections you can get. But
I asked this
I don't know what
question.
they were. Yeah, you asked this question before. But the light transform just takes, does like half a shadow, right? It takes, say, h to 1 minus h.
Right.
Yeah.
Did you say, or did I ask this question before, make sure I got the answer right, that the shadow on O3 halves minus a half, for example, doesn't take it to the melon. It's not the same as the melon primary with O a half, O minus a half, 3 halves, right?
Sorry, you are talking in terms of h, I guess.
Yeah, if h and h bar are 3 halves minus a half, the two sides of your diamond, you said they're related by shadow, but only one side is a melon primary. Is that right?
Yeah, either the left or the right, depending on which helicity you're looking at. And
those two things can't be identified? The shadow?
Well, I mean, if you add the top of the diamond, then you can say doing a shadow, like either the non-shadow or the shadow is obsolete because you can descend to either one. But that's including the top of the diamond guy. To arrive at the bottom corner, which gives to the soft operator, you only need one corner, right?
Right.
And if you have the top, the top corner, you can.
My question is: Are there two of these diamonds? One where the leftmost entry is O3 halves minus a half, and another where it's the shadow of O minus a half, 3 halves? Or are those things identified?
So there are there are 4 diamonds, let's say, because there's the goldstone diamond and there's the memory diamond. And then for each of those, there is, okay, it's the genoid for the delta equals 1 case, but let's say the sublevels of graviton. Then for each helicity, there's 1 diamond. And then this is for, say, the goldstone case. And then you have also the symplectic partners, which also have their diamonds. Yeah, and by descendancy and shadows, you can go within one, you fix, let's say, the left corner with 1 helicity, then you get 1 diamond. And then you fix the opposite helicity, you get another diamond.
And what labels the tops of the 4 tops of the 4 diamonds?
What, how do you mean? So there will also be delta J or HH bar that labels it. And also the 4D spin is no longer equal to the 2D spin, but you can figure that out from how it descends. So from the representation theory, you will get what kind of values of the 4D spin S, the conformal dimension delta, and the 2D spin J can appear in each diamond once you start from one place.
I'm just saying somebody's.
Sorry, I just wanted to understand. I think you said it, but maybe I didn't catch it. Is it true that the melon operator with dimension delta is the shadow transform of the melon operator with dimension d minus delta? Is this statement true or false?
Once you fix the helicity too, yeah. So for example, for the subleadings of graviton, because that's the non-degenerate case, on one side you have the dimension 0, and let's say helicity, well, the helicity for the radiative states, that for the helicity, I mean, the helicity is the same as the 2D spin. So let's say you take the negative helicity and delta equals 0, then its shadow is the, well, the shadow Mellin primary with dimension 2 and helicity plus 2. And
but
so
the shadow Mellin primary is not the same as the Mellin. You can also construct the Mellin primary with dimension 0.
Yes, you can do that too,
Those
but that's done in the memory
objects.
diamond. So there's the Goldstone diamond, which has the shadow mode, which has dimension 2, and then either plus or minus helicity. Fix the helicity, then you get its shadow, which is dimension 0 and opposite helicity because the shadow flips it. Those two, when you compute the 2D operator associated to that, picks out for you the stress tensor and its shadow. And then then you have also the memory wave function, which will be the so these are the Goldstone wave functions, which then in a product give you the stress tensor and its shadow. And then there's also the memory wave function diamond, which would then give you the the symplectic partners of the currents of the symmetry generators.
So this is very
true. It's certainly not true if you're at non-integer weights, what Prahar was saying, but it might be true at integer weights that the wave function that you get by Mellin transforming the Mellin primary of O3/2 minus a half, it's the same as the shadow of the wave function that you get from O. That's what you're asking, right, Prahar?
That is what I was asking. I was asking generally, but I think, actually, but I do think it's generally true for the massive operators. This is actually where my confusion came from. I do think it is true for the massive conformal, massive Mellin operators, that the Mellin operator with dimension delta is the shadow transform of the Mellin operator with dimension d minus delta.
Yeah, okay. I was talking just about the massless case. Yeah. Any more comments, questions?
I think perhaps the top and bottom of your diamonds are light transforms, because it's sort of the only thing you can do to change the weights and get something that's like primary besides shadow.
Yeah, that was raised, I think, by Andy in Sabrina's talk before. Yeah. Let's see.
So how it works for the principal series? So we have 1 plus I lambda, Felicity plus, and then you have a dimension 1 minus I lambda, Felicity minus. So what's the difference between the shadow and just you could start between the operator, let's say, okay, so there is a potential doubling problem, yes? So is it something that one should be worried or not?
Sorry, can you repeat that?
No, but it's not more related to generic case, not soft case. But we have a for principal series is 1 plus I lambda, and here's the plus, and then on the other hand, so with shadow we have a 1 minus I lambda, but here's the minus, yes. So we have just changing the sign of lambda in some way, yes, and changing helicity. So is it a separate? Is it a new operator or
you're talking about massless or massive?
How to distinguish between shadow and the operator is something which you start from the very beginning with You have positive lambda, you have negative lambda, and just with helix.
Yeah.
Yeah. So
I think for massive operators, they are the same operator.
Yeah, he was talking about massless, I think, since he's talking about helicity.
Yeah, but for massless, I don't know.
I mean, for massless, you can use either basis, right? Or you pick your favorite mix of things, which is, I guess, one of the questions on the board there. What's the best mix of wave functions that gives us the nicest features? Yeah. And maybe different questions are nicer in different bases. Like I think that we discussed the other day that the soft theorem's equivalence between the one-to-one map between soft theorem and the water densities is for the non-shadow, while for the shadow you get the celestial currents like the stress tensor and SUSY current and so on.
Sorry, I have a probably stupid question, but I don't know. Do we know that shadow and light transforms exhaust the integral transforms that give rise to new conformal bases, especially in 2D? Or could there be more conformal bases?
I can give you a perspective on this from higher D. I don't know if there's something special that happens in 2D. So where these transforms come from is that there is a Z2 cube symmetry for the quadratic and cubic Casimirs of the conformal group, just based on representation theory. One of them is a shadow transform, and the other is the light transform. And the third Z2 is just a combination of light plus shadow transform. And then there's a nice group symmetry in there. So as at least in higher dimensions, my understanding is that there are no other transforms to do.
But that's what I thought right now. But what's the Weil group associated to Virasoro? Can we have some other, like in 2D? Has anyone checked?
Those are the multi-particle states, right? So it's a little.
No, these are just taking you from one representation of the conformal group to another, but preserving the Casimirs, so the labels.
I know, but I'm saying if you're talking about Virasoro, right, in bulk 4D, that means you're talking about, single particle hard stage dressed with soft gravitons. So they're.
Right. So there are no more bases to discover, I suppose. At least we can rest easy with that.
There's an integer basis that Andy discussed. That's not related to the principal series basis, right?
Well, you can deform the contour, right?
You can deform it, yes.
But since, in principle, you can deform it to the whole complex plane, but then the question is what singles out that you should land on the integers or the half integers if you want to include fermions. So there should be something that tells you that that's better than just any complex value. Or it would be nice if there was something like that.
Well, that's where the poles and the scattering amplitudes are. So if we have a scattering amplitude and we write it on the things on the unitary principal series, and we start deforming the contours around, they'll get hung up on those poles, and we.
Right, but if you just started from the wave functions, you wouldn't necessarily.
No. So one of the ways you can constrain it, actually, it turns out you're supposed to require that the basis transformation is invertible, so that you can actually construct normal scattering amplitudes from celestial basis, and indeed that. And then you also have to, well, I suppose you also might want to impose that the Mellin basis operators are normalizable, say in the KG norm. And indeed that reduces you down to basically just two choices, either the principal series or delta is real. I don't know how to further go from there to integer. I think if you further assume, for instance, that the scattering amplitude is analytic in omega, which we know is not really the right assumption, but in a soft expansion, if there's no log terms in the soft expansion, if we assume that, then you can further reduce it down to delta being pure integer. And I think the presence of log terms or non-analyticity in omega in scattering amplitude actually perhaps suggests that we should be considering delta real instead of just integer. All I can tell you, the only fact that I can tell you is that if you require invertibility and normalizability, then the two options are real axis or principal series axis.
You think you might need the whole real axis? Is that what you're saying?
I'm not, that's what you naively get. There may be additional constraints that one would like to impose to further reduce it to Z. That's not something that I have, that's not something that I've done or seen. Just at this very simplistic level of requiring invertibility and normalizability. These are the two options that show up. Perhaps there are additional constraints that one should be thinking about as well.
Any more thoughts?
Yeah, the shadow involves a multiplication just by x squared to the 1 minus delta. So when delta is exactly 1, that factor becomes trivial.
Mm-hmm.
So that would suggest that the shadow of O 3/2 minus 1/2 is the same as O minus 1/2 3/2. Not for all the diamonds, but just for diamonds with delta equal.
Yeah, except the helicity flips, right? So it's not exactly the same.
Right, the helicity flips. The shadow of O 3/2 minus 1/2 is O minus 1/2 3/2. So there aren't independent. The positive helicity and negative helicity things at this integer are not independent, which is pretty weird.
Andy, I didn't understand why you said the kernel becomes trivial, but why do you think the integral localizes?
Well, I'm just looking at this. I just looked up this formula in 6.6.
Yeah.
It just says that it Pistersky.
Yeah, that applies only for massive particles.
No, this is the graviton.
Oh.
In massive particle, yeah, it's so there's something special that happens when delta is 1.
Mm-hmm.
In general, positive helicity and negative helicity are independent, but at delta equals 1, there's something weird that happens.
Yeah, as I mentioned yesterday, for delta equal to 1, and if the spin of the particle is actually either 1 or 2, but only for these two special cases, the shadow transform turns out to localize up to the spin transform. The helicity changes, but it's a local map. That works for spin 1 and spin 2 particles.
Yeah, so the soft operator that's at the bottom of the diamond, for all the cases that are not degenerate, they will just have like the derivatives acting on one of the helicity creation relation operators. But then in the case where delta equals 1 for both spin 1 and spin 2, then you get this degeneracy and you get contributions from both. That's another way that this appears. So if you plug in the wave function and compute the operator from the wave functions from the inner product, then you get both. I think at some point we have to stop the recording because the upload to the website will be enormous. But we can continue discussing. I don't know, Angelos, how much space do we have to?
We're fine, but I think it will be a problem. It's going to take more time to upload it back to YouTube. That's where it's going to be a problem. I'm going to stop it now. I can stop the recording.